Okay, so I hope all of you got your test results back with the corrections. If you want to see me work anything, I'll be glad to do that. I've got the test up here blank and I can go work it out. Does anybody have any requests? My hand's about to fall off because I graded all of those with a mouse, and that just, that's not as easy as a pencil. Anybody, anything? How many of you guys I got here right now? Got 18 of you. One thing I did want to point out is I didn't mean for this problem here to be so difficult. Let me show you what's difficult about problem B of number 4. I'm going to draw this for you. Make it pretty big. This particular cardioid has the point, the big part of the heart back on theta is pi, because the cosine of pi is -1. So when theta is pi, it's got that big part of the heart back there. And then this is a circle of diameter 1 over here. And so what I should have asked for was to get inside the cardioid and outside the circle. Yeah, inside the cardioid and outside the circle. There's a problem with that because inside the cardioid and outside the circle is this. Most of you found the point of intersection by setting these two equal to one another. You get 1 minus cosine of theta equal to the cosine of theta when the cosine of theta is 1/2. And so that occurs at pi over 3 and negative pi over 3. This is the negative pi over 3 here, and this is pi over 3. But I don't know if you can see the problem. If you just integrate the cardioid from there to there, if you compute this integral here, integral from negative pi over 3 to pi over 3 of the area of the cardioid. Oops, I should go the other way. If I want to go that way, I need to go to not pi over 3. I need to go to what? What is corresponding there? I need to go the way I've drawn my arrow. From pi over 3, let's see, that would be 5 pi over 3. Agree? To get this part from here to here, and that gets all of the cardioid. But now I need to take out this little piece right here and this little piece right there. And so what I need to do is integrate from pi thirds to where the circle closes up, which is at pi halves, just to get this little sliver out of there. And then I've got to double it to take it out from the bottom as well. So I can't write this as one integral. I'm going to get the area of the cardioid, which I shaded with the red slashes. But now to take out the solid red colored part, then I subtract the area of the circle from pi over 3 to pi halves to get this circle to close in over here of the cosine of theta squared d theta. But then I've got to do that twice. So that times 2. Do you see why that is? You can't do it with a single integral. So nobody got it all the way through. And I felt badly that I had a bonus that didn't work out very easily. So maybe next test I'll give you 2 bonuses and you get a chance to get some of these points back. How's that sound? Because many of us just tried to do this with one integral and you can't because we got to take off just a smidgen of that circle, not the whole circle. Make sense?
Yes.
Okay. Do you need to see anything else from the test? Anybody? You're happy, 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 happy? Okay, then we're in chapter 7. And in chapter 7, our primary purpose in life is to integrate. So I got to make sure that you know what it is that you're integrating and not integrating. So I'm going to go over the integrals you know how to do. So let's see, where is that handout? Review of integrals right here. And so first I'm going to write down the integrals that you already know. Give me a blank page. Oh, it just keeps reproducing that dang page. Well, that's not good. Let me just start a blank one. No, I don't want to go back there. Quit. Okay, give me a blank one here. There we go. I don't want dotted paper. Let's go with squared paper. Okay, so here's section 7.1. And this is a review of integration. So we had our basic integrals for x to a power, our 6 trig functions, our inverse trig functions, e to the x, and the natural log of x. And then we had the general version of them with the Udu substitution. So we know how to integrate u to a power. Where u is some function of x, and du is the derivative of that function times dx in all of the problems that I'm going to write. Then you've got your 6 trig integrals. Most of us probably remember how to integrate the sine of u, but we always kind of get mixed up. Is that a cosine or is that a negative cosine? Who remembers?
Negative cosine.
Good job. And then the integral of the cosine is a positive sign. Then we had the integral of what? We had the integral of secant squared of u, the function whose derivative is secant squared is the tangent. Then we had the integral of the secant of u times the tangent of u, and the function who has that as its derivative is a secant. Let's see, then we had a similar one for cosecant squared of u, and that one was minus the cotangent of u. And then mimicking this one, we have a cosecant of u, cotangent of u du to be minus the cosecant of u. So there are 6 trig functions. Today we're going to add to them an integral of the tangent of u and an integral of the cotangent of u. Then we had our natural log function, 1 over u du, integrates as the natural log of the absolute value of u. And then integral of e to the u du integrates as e to the u. Then we had 3 inverse trig functions. Let's see if I can get them all to fit on here. The integral of, let's see, the arctangent one looked like 1 over x squared plus 1. Oops, I want u's. 1 over u squared plus 1 du. And that was the arctangent of u. Hopefully today I'll give you a more general version of that one. The one that was the arc sine had a square root under here. And under the square root was a 1 minus u squared du. And so that was the arc sine of u. And then I don't have room for the other one, so let me squeeze it up in here. The other one was the arc secant, and it looked like the integral of 1 over, it had a u out here, sometimes an absolute value, sometimes not. And then a square root of u squared minus 1 du. And that was the arc secant of u. We don't need an inverse cotangent or an inverse cosine or an inverse cosecant, because they look like these three right here, but with a minus sign on top. So in other words, minus 1 over u squared plus 1 is an arc cotangent. But who cares? Just make it a negative arctangent. Okay? So we don't need the other 6. Those are the integrals you know how to do. Whether you know how to do them or not. So keep those looking at you, because now I'm going to do some of these. I'm going to bring back my little handout from section 7.1, and we're going to work through a few of these. I'm even going to add a few more than what I've got on that handout. Let me make sure you got all this down. That's hard to tell on a Zoom call. Are we getting used to this not coming to class stuff? Have you like worn the same sweats for 5 days in a row?
Relatable.
Okay, so I'm gonna open up the other document here. I do need to have this the other way so that I can put this on YouTube. So let me turn it that way. And now I'm going back and I'm going to open, let me close that one. And I want to open the review of integrals. So the first one, the integral of the sine of 5x, is something we know how to do. It looks like a sine of u. Some of us can skip the step where we call u the 5x. I'm going to put it in just because it is a review. And then we can take the derivative of that and we'll just get a 5 times dx. And so if I solve this equation to match that dx, I'm going to have a 1/5 du substitute in for the dx. So our substitution integral becomes the sine of u times 1/5 du. But that 1/5 is baggage. I'm going to take it. It's a constant. I'm going to put it in front. And then we're left integrating 1/5 the sine of u du. We said that one was the one that was the minus cosine of u. And so finally, we'll put the 5x back in, and we'll have a negative 1/5 cosine of 5x plus c. So was that too easy? Most of us could go straight from here, from the first line to the last line without putting any steps down, and I don't mind that at all, as long as you know we should get a 1/5. Just like on the exam when we were integrating a cosine squared of 3x. You know the formula for the cosine squared of u, so that gave us a 1/3 out front. So make sure you can remember the constants. All right, now let's look at number 2 here. It's almost a u du, right? If I take u to be the secant of x, its derivative is the secant of x times the tangent of x. But I don't have secant times tangent, I have secant plus the tangent. So it's not a u du integral the way it sits. So we got to try something else. And I guess the only thing left to try is to multiply it out. Or we can go to sines and cosines. But I think if we multiply it out, you might see something that you like. If I distribute the secant through there, we're going to get a secant squared of x plus a secant x times a tangent of x. Those are both familiar to me. I know a function whose derivative is secant squared, and I know another function whose derivative is secant tangent. So I know the antiderivatives of these if I did them one at a time. The function whose derivative is secant squared would be a tangent. So the antiderivative of secant squared is tangent of x. Then the function that has secant tangent times its derivative is the secant of x. So once I multiply it out, I've got it. And that's kind of a hint to how I'm going to do problem number 3. We don't have a formula for the integral of the secant of x all by itself. We have two formulas, one with a secant squared, one with a secant tangent, but not one with a secant all by itself. We can try writing that in terms of cosine, but then I'd have the integral of 1 over cosine. And I can't integrate that. I can't integrate a cosine unless I have a sine in the integral. So it doesn't help that way. So here's our trick. We're going to be integrating the secant of x a gazillion times in chapter 7. So I'm going to derive the formula for it, and you're going to memorize the formula for it. And the trick is to use the idea from the above problem. I'm going to take this integrand and I'm going to multiply by 1. Because I can. We can multiply anything by 1. But I'm going to multiply it by 1 in this form. I'm going to multiply it by the secant of x plus the tangent of x over itself. So this is a, one of our, it's a trick. It's a trick when you see it the first time, but it's a technique when you see it twice. So this is your first time seeing it, so it's just a trick. When I do that, if I multiply the top out, I'm going to have the same integral that I had a second ago. So I'm going to multiply the top out and get secant squared of x plus the secant of x times the tangent of x. And then on the bottom, I've got the secant of x plus the tangent of x, which was what I got as my value of that integral that appears on top in the previous problem. When I integrated secant squared times the tangent, I got tangent plus the secant. That tells me I've got a UDU integral here. I can take u to be the denominator, and du is going to be the numerator. See, this is u right here. All of this stuff is du. And this little multiplying by 1 trick gave me a 1 over u du integral. And that's just the natural log of u. We should put it in absolute value, because in this case, my u term can be positive or negative. My u term was the secant of x plus the tangent of x. So what I'm going to do is go back to that formula sheet that I started the class with, and I'm going to add this as a formula. Then I'm going to derive the formula for the integral of the cosecant by doing the same trick. And I'm going to derive the formulas for the integral of the tangent and the cotangent. Those are also UDU integrals. Easier than this one, though. So let me pop back to the other page here. These are my formulas. I'm going to add the one that I just did, that the integral of the secant of u du is the natural log of the secant of u plus the tangent of u plus c. And now I'm going to do the same trick to get you a formula for the integral of the cosecant of u. Let me swap to blue. Okay, we're going to do that same trick. To find the integral of the cosecant of x dx, we multiply by 1 in the form of the cosecant of x plus the cotangent of x. Put on the top and the bottom. So I can make this a single fraction here. And if I multiply out the top, I'm going to get cosecant squared of x plus cosecant of x cotangent of x. Just like we did before. And we did that, and it turned out that the derivative of the bottom was essentially the stuff on the top. That's going to happen again. I'm going to pick u to be the bottom, and then its derivative, it's going to be negative. Derivative cosecant is negative cosecant of x cotangent of x. And the derivative cotangent is a negative cosecant squared of x. So it's the same stuff I have in the numerator up here, written backwards with a minus sign. So I can just move the minus sign over here with the du, and then change the order in which these are written. And my original integral is going to become a minus du over u. So here's the minus, and then there's my 1 over u du. And so we get a logarithm again, but this time with a minus sign, where the u term is the cosecant of x plus the cotangent of x. Except for this is in u, so let me go back to, oh, nope, you're right, they're x's. There we go. So I'm going to go back up here and write that as a formula for you guys to learn. The integral of the cosecant of u times the cotangent of u du is minus the natural log of the absolute value of the cosecant of u plus the cotangent of u. So these guys, the secant and the cosecant, are cofunctions. They have derivatives that look alike, and they have antiderivatives that look alike. The same is going to be true with the tangent and the cotangent. Let's find the integral of the tangent down here, and then I'll go back and fill that in. The integral of the tangent of x. You may have done this one in Cal 1 because it's a basic substitution integral. You just rewrite the tangent as the sine of x over the cosine of x. A du du integral appears when one of the terms has as its derivative the other term. Here, the derivative of the cosine is the sine. We always want the du term on top. So I'm going to pick u to be the cosine of x. And then du is minus the sine of x dx. And so my integral is minus the integral of 1 over u du. And we get minus the natural log of the absolute value of u, where u was the cosine of x. So I'm going to go back up here and write this in my formula, that the integral of the tangent of u is minus the natural log of the absolute value of the cosine of u. That one's easy to remember. There's also an alternate version of that. This minus the natural log of the cosine of u is equivalent to the natural log of the secant of u. Why? Why can I go from the minus the natural log of cosine to the natural log of secant?
Because cosine to the -1 is equal to secant.
That's right. Cosine raised to the -1 as being 1 over cosine, not the inverse of cosine. Remember the property of logarithms that allows you to take coefficients up as powers. So cosine raised to the -1 power is the same as 1 over cosine, which is secant. To me, it's more helpful to remember it is minus the natural log of cosine, because when we do a definite integral, I'm more familiar with the values of the cosine right off the bat than I am the secants. All right, so let's do the next one in our head. The cotangent is the cosine over the sine. So if we take u to be the bottom, du is the top. And that's just the integral of 1 over u du. So that's another logarithm. But remember, the bottom was a sine this time. And so the integral of the cotangent of u is the natural log of the sine of u. Again, it's nice that the tangent and the cotangent have integrals that look like each other because they have derivatives that look like each other. Okay, so now there's 4 more for you to learn. And then we've got the other 2 that we did over and over again in chapter 6. The integral of the sine squared of u and the integral of the cosine squared of u. Those 2 are in our list of integrals that we know how to do. So let's go back to the handout and see what we can do with the other ones. So I'm looking at number 4, and I'm trying to figure out if this looks like any of the integrals on that previous page, and if I have the derivative of any term in here. I want to see if there's any way at all to write that as a u du integral. Does anybody see anything that helps you?
1 plus secant squared is equal to tangent squared.
It almost is equal to tangent squared. Let me show you the Pythagorean identity. I know sine squared plus cosine squared is 1. If I want the Pythagorean identity for tangent, I just take that and divide every term by cosine squared. And then I'll get that the tangent squared of x plus 1 is the secant squared of x. I have 1 plus the secant squared, so that's not quite the tangent. Secant squared minus 1 would be the tangent squared. But that was a really nice try. I can't take u to be the entire denominator because the derivative of 1 plus secant squared of x is not going to be in the integral, but let's try it.
Can you take u to be secant squared, and the derivative of secant squared is secant tangent, and that's the
Close. I don't want secant squared,
secant.
just the secant, because the derivative of secant squared will have a 2 secant of x.
Yeah.
Times secant tangent. So that's a good eye. That's what I wanted you to see. I want you to look at this denominator as a 1 plus u squared. Just take u to be the secant of x. And then the du is the numerator. And so this integral becomes, so the whole numerator is going to go out with the du term. And the denominator, I'm only replacing the secant. So that becomes a 1 plus u squared. What was the integral of 1 plus u squared?
Arctangent.
That's an arctangent of u, where u is the secant of x. Good, good. I'm glad you saw that. Because if you saw that, you might see the next one as well. I want you to compare the next one. Compare the next one to this integral, e to the 2x over the square root of 1 minus e to the 2x. Just made a subtle change. I know that when I take the derivative of an e to the 2x, in that derivative, I'm going to have an e to the 2x times a 2, but I'll have an e to the 2x. So that second integral that I wrote, the entire quantity under the square root sign would be the u. Because its derivative, for the most part, is going to be in the numerator. Right? Derivative of an e to the 2x has an e to the 2x in it. And so I can do that second integral by taking u to be all the stuff under the radical sign. And then my numerator is the du. So I integrate that as a u to the negative 1/2 du, which becomes, let's see, add 1 and I get u to the positive 1/2, divide by 1/2 gives me a 2 here. So I just get minus the square root of u, where u was 1 minus e to the 2x. So the moral of the story is, if I've got an e to a power appearing in the same way in the function and out of the function, then I've got a u du integral. But in this one, I don't have that. I've got an e to the 4x down here, but an e to the 2x up there. So it's not going to work like my pretty blue problem. You got any suggestions?
Make e to the 4x, e to the 2x to the second power.
That's perfect. Recognize that e to the 4x is the square of e to the 2x. So now I've got the same power on e appearing top and bottom. But this time when I choose u, I only take u to be the stuff right here in the parentheses. I take u to be the e to the 2x only. And so its derivative is the numerator times 2. So I'm going to get another 1/2 du. But this time when I rewrite my integral, my numerator is going to be the du term. My denominator will be 1 minus u squared under a square root sign. That's one of the integrals we had on the previous page. That's an inverse trig function. Which one?
Arc sine of u?
Yep, that's an arc sine of u. So you get negative 1/2 times the arc sine of u. But since I'm at the bottom of the page, I'm going to go ahead and fill in my u as e to the 2x. So you got to keep your eye out for things like that. If you've got an e to a power and the same e to the powers in the integral, then you grab the whole part of the composite function as u. But if they differ by a power of 2, then you try to look at it as a quantity squared. Look for your inverse trig functions. Any questions so far? Oh, Ashton, did you ask something? Ask me a little bit louder.
Yeah, sorry. Where does the negative sign at the bottom come from?
The negative sign at the bottom. Yeah, I don't think I have a negative sign at the bottom, do I? I'm going pretty fast. Had like 5 cups of coffee today. I can do this climbing the walls. Thank you for finding that. Anything else? Well, lucky for you, I got a page 2. So here we go. All right, we're at the top there, number 6. I've got an x squared over an x squared plus 4. Now, if I just had this integral, 1 over x squared plus 4, then I can treat that like an inverse tangent. We're going to have to do something about the 4, but I can show you how to handle that. But I don't have a 1 there. I have an x squared there. If I had an x on top, then I have a u du integral. Do you recognize that? If I have an x on top, then that's 1 degree less than the denominator, so I would have a 1 over u du integral. Well, I have neither of those 2 cases here. So what do I do?
You could multiply by 4 over 1/4.
Let's see. Which one? This one here?
On 6,
Or are we going here? Why would I multiply it by 1/4?
because then whenever you derive your x squared plus 4, you'll get 2x dx, and then you can get a 4x squared on top, which will be 2x squared. So then we'll have u squared on top over du.
But you don't want your du on the bottom. Du always has to be on top. Let me use your idea first to do this one. Let's do this one over here in the margin. We have the formula that has a 1 in that last slot. I want to make it more general so that it look like an arctangent integral. So when there's a number here other than a 1. So in other words, I want to derive a formula for 1 over a squared plus u squared. So I'm going to do that. I'm going to do it. I guess I'm going to do it right here and then I'll erase it. So let's do the 1 over x squared plus 4. I'm going to take the denominator and I'm going to factor out a 4 from the bottom. But since there's not a 4 on the x squared, when I factor out a 4, I'm essentially dividing by a 4. Now this 4 right here is a constant. I can pull it out front as a factor of 1/4. This 4 I can write as a factor of 1/4 in front of the x squared. I can even go further. I can take the product of 1/4 x squared and I can write it as a 1/2 times x quantity squared. And now that's a u du integral, where u is the 1/2 x and du is 1/2 times dx, so 2 du is dx. This too I'm going to write out front with the 1/4, And so that's going to give me a 1/2 out here. The 1/2 x squared becomes u squared. And now this gives me an arctangent. It's the arctangent of u, where u is 1/2 x. So I don't want to have to do all those steps when I have something like this integral right up here. If I've got a number squared plus the variable squared, I want to jump straight down to this. And so our formula is, we'll get an arctangent all right, but it'll have a factor of 1 over whatever that number is that's squared here. And then you get the arctangent of u divided by a, and then plus c. So I'm going to go back and add that as one of our formulas, a more general formula of the arctangent of X formula. So let me go back to that other handout. Come on, right there. I want to take this junk away. Now let's just add it to the next page right here. These three integrals have a more general form. The integral of 1 over a squared plus u squared du is the one I just derived as a 1 over a arctangent of u divided by a plus c. The more general form for the inverse sign had a 1 minus u squared. Well, I can have an a squared minus a u squared in here. And that one's going to give us an arc sine of u divided by a plus c. It's not going to give us the 1 over a out front. The more general form of the inverse secant has a u right here. Sorry. And then the square root of u squared minus a squared du. That one does have a 1 over a out front, and that's the arcsecant of u over a. These more general forms are the ones that we'll use more often. These are the ones you should really learn. Oops, stay. Okay, they're more general than the ones I wrote earlier on. Now we're going to have some version of that first one back on that problem on the other handout. So I'm going to fly back to the other handout here. If I had the one there, fine. Then I jump right to that arctangent. If I have an x there, then that's a u du integral. But I have neither of those cases. So we got to try something else. If I have a fraction, for instance, like 25 over 4, that's called an improper fraction because the numerator is bigger than the denominator. 25 over 4 can be written as a mixed fraction. It's 6 1/4. This is an algebraic version of a mixed fraction. I can divide that and find the whole part plus the remainder over the divisor. Clear this bad boy here so I got some room. So we're going to make that a general rule. If the degree on top is greater than or equal to the degree on the bottom, we have an improper fraction, and you should divide first. if you remember your polynomial division. It's a one-step division. The one on the bottom is the divisor. The one on the top is the dividend. And I know that if I multiply x squared by 1, I get x squared. So my quotient term is just a 1. And then I subtract that line from the line above it, and that -4 is my remainder, which is the fractional part as a fraction of the divisor. That tells me that my original integral is the same as 1 plus the remainder over the divisor. And then I can integrate those separately. The integral of the 1 with respect to x is just x. The second integral is the one we did just a second ago, but it's got the 4 there. I just pull the 4 out. And then the integral of 1 over x squared plus 4, that's the arctangent. So I get a 1 over 2 arctangent of x over 2 plus the c. And that's it. You like that? I could have also added 0 instead of doing this division thing. Take a look at my fraction at the beginning. Here's another way. I can add 4 and subtract 4. And then I can make 2 integrals out of that. And that takes me back to here. There's my 1, and there's my -4 over x squared plus 4. So if you're not fond of polynomial division, you can just add and subtract the same number. Every one of these on here can be done with some sort of algebra. So we're looking at number 7 there. If I didn't have that 8x in there, if that was gone, x squared plus 25, that's an inverse tangent integral. But that's not gone because look, there it is. When I see a polynomial like that, I'm awful tempted to factor it. But are there factors of 25 that add to 8?
No.
Nah. So I can't factor it with my traditional binomial factoring. What's another thing that comes to your mind?
Quadratic formula.
Close. I don't want to know the zeros, but I do want to do something quadratic-ish.
Complete the square?
Complete the square. Atta baby. Let's see if you remember how to complete the square. To complete the square, I group the x squared and the 8x together, and I leave a gap. And then I've got the 25, and I'm going to add and subtract the same number. But I'm going to add and subtract the number that makes this first batch a perfect square. I'm looking for some number to put in this box that has 2 identical factors that add to 8. You got them?
16.
16. I put a 16 there and a 16 there. Then the first batch of terms factors as x plus 4 all squared. And then 25 minus 16 gives me a 9. Did that help any? Yeah, if I hide the x plus 4, if I just hide the x plus 4, I have 1 over u squared plus 9. That's an inverse tangent. Well, I don't have to hide it. I can just call it u. derivative is just a constant, so I've got it. This becomes the integral of 1 over u squared plus 9 du, and that's the general form of the arctangent integral. The 9 is the a squared, so I think of 9 as 3 squared. And my general formula has a 1 over the 3 out here, arctangent of u over 3 in here, where u is the x plus 4. So completing the square is now in your bag of tricks. We've got dividing, we've got completing the square, neither of which works at the next one. And we've done problems like number 9 in Calculus 1. But I'm gonna have to save those for Friday because I can't waste your day any longer than I already have. What else you got to do today? Nothing. Come on, I'm getting ready to go outside and shovel the driveway and the sidewalk. And I have an extra
No.
shovel. What?
We're gonna go play in the snow.
I haven't moved
So much homework,
my house.
I'm busy.
I have 2 more classes.
2 more classes, but they're online. Doesn't your rumpus get sore?
Yes, I hate it. That's why I signed up for in-person classes, and yet here we are.
No, I'm sitting on like 3 pillows because I'm so tired of sitting.
It's really not fun at all.
Well, that's why I'm going to go out and shovel the sidewalk. It is not fun. And I think when my phone rang, that might have been another one of those tech alerts.
Classes are canceled tomorrow. In person.
Classes are canceled tomorrow. Wow, I'm almost certain we'll be back in class on Friday.
Let's hope so.
Really hope so.
Really, if not, let's just meet at my house.
I'll make them
We'll
walk.
have chips and salsa and calculus.
There we go.
How about that? That's all that's
Sounds
left in
good.
my house now are chips. We've eaten everything else. So we're having nachos for dinner tonight.
Oh,
Sounds good.
All right, that's my specialty. Okay, guys, I'm gonna let you go and go have a good rest of the day. I know I did this kind of fast, but I'm gonna post this on Blackboard, and so you can go back and pick up all the details. And sorry, my handwriting was so messy today. It's the 5 cups of coffee.
Dr.
Yeah.
Earlier, somebody was saying something about a negative sign. Where exactly was that at?
Where was it? I think
right there on question 5.
here I had a minus sign accidentally here, and I just erased it. So there's no minus sign there. Nothing was negative on number 5.
Take care, Professor.
All right, you guys go on. Have a good day.
Thank you. Have a good day.
Thank you.
Thank you.